Welcome to Unit 3, Electrons Concept 1 Notes, and this is going to be an introduction to electrons. So first, really, I feel like if you boil chemistry down, it's all about the electrons. I always say in my biology classes that biology is all about the proteins. So proteins are to biology as electrons are to chemistry. They are absolutely essential and foundational to literally every single thing we will learn. So you were introduced to the electron in our atom unit, which we did previously to this, but now we're going to really dive a lot deeper into electrons, how they behave, and why that impacts the atom and how the atom as a whole is going to behave. So remember, electrons, we can, abbreviate them as an E with this little minus sign since they have a negative charge. They are subatomic particles like protons, which are positive, and neutrons, which are neutral. But they don't really behave like particles. So Bohr, in our Bohr models, which we were drawing in our last unit, he predicted them to act with his orbital model. He predicted that they would act like particles and they would move in these fixed orbits kind of around the nucleus. And that's nice and it's easy to draw atoms that way, but that's not really how they're acting. Instead, they're acting a lot more like waves do. And so that makes this model, our electron cloud model, a lot more accurate description of how the atom, kind of is structured. So just a little reminder, the atom is held together by forces. So mainly there's an electromagnetic force, which can be attractive for opposite charges and repulsive for like charges. And then there's also a strong nuclear force that's happening because of the quarks that are in there, which again, we learned about in our last unit. But one thing that you might be thinking is, okay, so if there's an electromagnetic force and opposites attract, why aren't the negative electrons pulled into the nucleus due to the attractive force since the nucleus is positive? Like, why aren't they just pulled in? And that is because electrons have insane amounts of energy, and this energy keeps them in constant motion around the nucleus. And the energy of an electron can change with radiant energy, also known as light energy, which is also known as electromagnetic radiation. Okay, so this is hopefully familiar to you from physical science, especially if you're one of my students and you had me for physical science prior to taking chemistry. Radiant energy, light energy, electromagnetic radiation, we're talking about the same thing here. So I need you to make sure that's like cemented in your brain that these are all the same thing, okay? So a refresher, what's electromagnetic radiation? It's a form of energy that exhibits wave-like behavior as it travels through space. So we're talking about light here. And there's different forms of electromagnetic radiation. There's different forms of this light energy. There are radio waves, microwaves, infrared waves, visible light, ultraviolet rays, X-rays, and gamma rays. I think often when we think of light, we're just thinking about visible light that we can see, but there's so many other things that are included in this. And they're referred to as electromagnetic because they have both electrical and magnetic properties. So that's where that electromagnetic comes from. Okay, so this is what we're seeing here. Now, if I want to refer to all these different types of electromagnetic radiation together, then I'm talking about the electromagnetic spectrum. So that's all of the different forms of radiant energy. They're on a spectrum and there's some patterns in this spectrum that I want to make sure you know. So first and foremost, like I said, all radiant energy travels as waves through empty space, but it does it at the speed of light. So all of these electromagnetic waves are light energy. They're traveling at the speed of light, which is represented by the letter C, and that's 3.0 times 10 to the 8th meters per second in a vacuum. That's 1 million meters per second. That's how fast light travels. So all of these have the same constant. They're traveling at the same speed. But there are some things that are different about them, and that's what we can quantify about them. We can look at their wavelength, their frequency, and their energy. And I'll correct this before I share this, but this F is what we use to represent frequency in physics. But with chemistry, we're going to use the Greek letter nu, which looks almost like a little V. And so that's what you're going to see on future subsequent slides. So I just want to point out that discrepancy really quick. But so again, we can quantify waves. We're going to look at how long they are, how frequently they're passing a point, which we'll define in a second, and then their energy. So looking at this spectrum, the longer wavelengths are the radio waves, and then the shorter wavelengths are here on the gamma ray side, which you can see because wavelengths are measured peak to peak, crest to crest, or trough to trough. So we can see that here, how they're more spread out, and then they're shorter here. On this end, though, if you have a longer wavelength, you have a lower frequency. The shorter wavelengths have the higher frequency. And then if you have a lower frequency, you're also going to have a lower energy. So these waves have lower energy. These waves have higher energy. So that's why we like this spectrum, because we can see anywhere on here, we can compare levels of energy, wavelengths, frequency, etc. Okay, so velocity, or the speed of a wave, can be calculated as wavelength times frequency. That's that corrected symbol that we're using in chemistry. We're going to use this V to represent frequency. And like we said, that the speed of light is C equals 3.0 times 10 to the 8th meters per second, then we can rewrite this equation for electromagnetic radiation. So for electromagnetic radiation, C equals wavelength times frequency. Again, wavelength is our unit for distance for measuring waves, and oftentimes that unit's going to be in nanometers. That's what we're going to see it as. And then our frequency is the number of waves that pass a given point in certain time, which is often measured in hertz or waves per second. Now, in this equation, though, because our speed of light is in meters per second, to use wavelength in this equation, it needs to be in meters. But oftentimes, because waves are so tiny, they're represented as nanometers. So that's something to keep an eye on, because you might need to convert from nanometers to meters. Okay, so let's talk about that relationship then between all these variables. Because this is constant, we can look at how, if this changes, what will happen to this. Okay, so wavelength and frequency have an inverse relationship, meaning as one goes up, the other goes down. So as you increase the wavelength, you're going to decrease the frequency, and vice versa. Frequency and energy have a direct relationship. So as one goes up, the other goes up. As one goes down, the other goes down. So if you have a higher frequency, then you have a higher energy. And if you think back to our last unit where we learned about nuclear chemistry and we learned about gamma rays, we saw that gamma rays, as opposed to like alpha or beta radiation, they have the greatest penetration because they have the highest energy and the highest frequency. And we see gamma rays here as well. Okay, so I know this is kind of a lot to take in. We're bringing in a lot of things from physical science, so hopefully some of it's familiar, even though it's a little bit different too. We're going to stop here in class and kind of just do some practice with this and digest it. But for the sake of the video, we're going to kind of keep moving forward because there's a couple other things I want to talk to you about. Because again, this whole concept is just an overall introduction to electrons. So okay, we've talked about the electromagnetic spectrum. We're going to practice it some more. But I need to make another connection with you between electrons and the EMS. And that is that electrons exist in specific energy levels. You know this because when we learned about atomic structure in our last unit, we talked about how the electron cloud is divided into shells or energy levels. So electrons exist in different energy levels in the electron cloud based on how much energy that they have. So however much energy that they typically have, that's their ground state. Now, when they absorb energy, they can then jump to a higher energy level, which means further away from the nucleus. And when they do that, we say that they're in their excited state. So let's say you have some matter, which has electrons in it. If it absorbs some electromagnetic radiation, some light energy, it can get excited and go from its ground state to then its excited state and jump to a higher energy level. But now, when it's in that excited state, it will not necessarily retain that energy forever. When it releases that excess energy, that it goes back to its ground state, it drops backwards. That excess energy that's released is emitted as light. So we can see a color there. And so we call this the emission spectrum. It is the spectrum of light that's released from excited atoms of an element. So when an element, gets heated and has that, it's absorbing that electromagnetic radiation, and then it's going to get excited and it's going to jump up a state. And then as it falls a state, it's going to release energy in the form of light, and we're going to see a color. And that's going to help us to identify different atoms. So I like to think about this as a ladder against a wall. And if I was in person teaching you this right now, I would prop up a ladder against the wall and I would start climbing up it. So consider the ground, like the floor of the classroom, that's like the nucleus. And then each rung on the ladder is like a different energy level. So the higher you go up the ladder, the further away from the nucleus you are. And the more energy it's going to take you to move further away from the nucleus. Because remember, you're having to overcome that attractive electromagnetic force that exists between the positive nucleus and the negative electrons. So to be further from the nucleus, you're going to need more energy. So the more energy an electron has, the further from the nucleus it can be, the further up the ladder it can be. Now, its ground state is whatever rung it normally just kind of sits on. But if it gains energy, if it absorbs energy, like if we apply electromagnetic radiation to it, it can gain enough energy to then jump energy levels and jump to the next rung on the ladder, further away up the ladder. And then if it loses energy, it will jump back down to its ground state and come closer to the nucleus. And that energy that it loses or releases is going to be given off as light. And we're going to see this in a lab that we are going to do together. So the amount of energy emitted is going to determine the color of light that is given off. Because if you remember, if we go back to, say, here, we can see that if we zoom in on the visible light spectrum, the red wavelengths are longer, the purple wavelengths are shorter. The red wavelengths have a lower frequency and the shorter have a higher frequency. So whatever color light is given off will tell us, the wavelength of that light. And so that's an interesting identifying factor, and it tells us how, if we know the wavelength, we know the frequency. If we know the frequency, we can know how much energy is given off. Okay, so now in class, we're going to stop and we're going to do a lab, and you're going to really see this, and it's going to make a ton more sense. But again, for the sake of the video, we're going to keep pressing on with our introduction to electrons. Okay, so now let's talk about electrons and what they have to do with stability. And again, we kind of introduced this in our last unit, but we're going to dive deeper in this one and even deeper in our next unit about chemical bonds. So first, remember, the nucleus of the atom, which has the protons and neutrons, it doesn't change much unless it's radioactive, which you hopefully remember from when we learned about nuclear chemistry and nuclear reactions, okay? So it's not changing much at all. Electrons, though, they're constantly moving within the atom. And so it's much easier to move electrons than it is to move protons or neutrons in order to change an atom. So what we see is that for an atom to become more stable, it will often transfer its electrons to form bonds by making compounds. So it's going to be transferred to form bonds to gain stability in the form of compounds. Now, I mentioned electrons are constantly moving. So that's where the Heisenberg uncertainty principle comes in. It is impossible to determine the position and the velocity of an electron or another particle simultaneously. There's just too much chaos going on here. But we do need to have somewhat of an idea of where electrons are in general so that then we can predict how they will behave. Because again, their behavior, their properties, how they're going to act is going to be so that they can garner some stability. That's what they're typically going to do. They want to be stable. And so we want to know where the electrons are because electrons impact stability. Now, the most important electrons that we need to know about are the valence electrons. Okay, so if you remember, these are the electrons in the outermost energy level of the atom. We call this the valence shell. So those are the ones that are going to most readily be shared, given, or taken from another atom in order to form a bond that's stable. We say that all the other electrons in the atom are core electrons. Now, for main group elements, so I'm talking about everything but those transition metals because those get a little tricky. They transition, which we'll talk about later in this unit. But if you remember from our last unit, the group number of our main group elements corresponds to the number of valence electrons. So if you're in group 2, you have 2 valence electrons. If you're in group 1, you have 1 valence electron. If you're in group 13, you have 3. 14, you have 4. 15, you have 5. 16, you have 6. 17, you have 7. That kind of thing. And this number is what's going to determine the behavior of the atoms because having the same number of valence electron gives these elements similar properties. That's why we see that all of the halogens, all of those elements in group 17 tend to act similarly and have similar properties because they have the same number of valence electrons. Now, we're going to get a lot more into periodic trends and these patterns and properties in concept 3, but for now, this is what's most important to know. Now, let's zoom in on stability a bit more. Atoms are most stable when they have full outer energy levels of electrons. Well, they have full energy levels in general, but we fill from the inside out. So we're talking every level, including that outer valence shell, is full. Oftentimes, this means 8. Okay, and so this is called the octet rule. It's the tendency of atoms to prefer to have 8 valence electrons. Now, exceptions here are hydrogen and helium. That's because they only have one energy level, and that inner energy level only holds 2e. So for them, stability is just 2e, but pretty much everything else is looking for 8. Now, think about the noble gases. They're in group 18. They are already stable because they have full energy levels of electrons already. So they're not very reactive. They're not going to form bonds readily because they don't need to. They're already stable. But other atoms want to be like those noble gases. So they're going to gain, lose, or share their valence electrons in bonds in order to become stable. And again, we have a whole unit coming up on this, but I have to introduce this now because we're talking all about the electrons, and electrons are what is doing this. Okay, so example. Look at this Bohr model of sodium. Notice sodium's in group 1. It has one valence electron. Sodium will give this electron to chlorine so that they can both be stable. It's going to form a bond because if you look at chlorine, chlorine's in group 17. Notice it has 7 valence electrons. It only needs one more to be stable. And sodium could gain 7 or it could just lose 1 to be stable. It makes much more sense for it to lose 1. And so that's what's going to happen. Sodium's going to give this 1 electron to chlorine. Chlorine's going to take that 1 electron from sodium. They're going to form a bond. And this is what makes the compound sodium chloride, NaCl, which is table salt. And so this is the kind of stuff we're going to be looking at a lot more in our next unit. But again, I really wanted to introduce it to you now. Because if an atom gains or loses electrons to become stable, it becomes an ion. Okay? An ion is an atom or molecule that has a charge due to having lost or gained electrons. Cations are positively charged ions that have lost E in order to become stable. Typically, we see this in metals. If you look at your periodic table, remember the metals make up kind of most of the left part of the periodic table. So they tend to only have, 1 or 2, maybe 3 valence electrons. So it makes more sense for them to lose those 1, 2, or 3 electrons to become stable than to gain, 5, 6, or 7 electrons. So let's look at magnesium as an example. It is in group 2. It has 2 valence electrons. So instead of trying to gain 6 to hit that octet rule and be stable, it's just going to lose these 2 to be stable. And that's going to make it a cation with a positive 2 charge because it now has 2 less electrons than it does protons. So we would write it as a cation as Mg with a plus 2 charge when it forms that cation. Okay, on the other hand, we have anions. These are negatively charged ions that have gained electrons in order to become stable. And this is what we typically see in nonmetals because, again, nonmetals are that right side of the periodic table. They're in groups 16 and 17 and 15. They have 5, 6, 7 valence electrons. It makes more sense for them to gain 1, 2, or 3 electrons than try to lose 5, 6, or 7 electrons. So look at oxygen here. It has 6 valence electrons, so it will need to gain 2 in order to be stable. And it's going to create an anion with a minus 2 charge because it's going to have 2 more electrons than it does protons, making its symbol O with a negative 2 charge when it is in its ion form. Now, these Bohr models are helpful. This helps us visualize where are the valence electrons, what's happening, that kind of thing. But they're also a little bit tedious. You don't need to draw that entire thing every time. Because remember, what really matters most when we're looking at how these atoms are going to behave is looking at their valence electrons. And so that's where Lewis structures are really helpful. Lewis structures are a convenient and simple way to represent an element and its valence electrons. All you do is you write the symbol and you use dots to represent the valence electrons. That's literally it. Instead of having to draw the whole thing with all the energy levels like you do for a Bohr model, you just do this. And so Lewis structures are also known as Lewis dot diagrams or electron dot diagrams. So if you see any of those terms, just know they are interchangeable. And again, they show us what the element is by showing the symbol, and then they show how many valence electrons it has by drawing those around the element. So here's how we draw them. When you're drawing them, instead of drawing the nucleus like you would in a Bohr model, you're literally just going to write the atomic symbol to represent the nucleus. Okay, so let's say we wanted to write a Lewis structure for nitrogen. We would really literally just draw an N to represent the nucleus. Okay, now to determine the number of valence electrons, we're going to look at the group number. So look at the periodic table. Notice that nitrogen is in group 15. That means it has 5 valence electrons. Now we're going to represent those valence electrons by drawing dots around the chemical symbol, one for each valence electron. But here's the key. We are going to fill one side at a time before we start pairing electrons up. And this is going to make more sense when we get to concept 2, why this happens. But for now, just follow this rule. Okay, so if there's 5 valence electrons, I'm going to put one on the top, one on each side before I pair them up again. So 1, 2, 3, 4, 5. And that is how I would draw the Lewis structure for nitrogen. Okay, so now I want you to try this for hydrogen, carbon, fluorine, and phosphorus. We will go over these in class, and then we are going to practice even more all of this together. So I hope this was a helpful introduction to electrons, and then we'll dive a little bit deeper into electrons in concept 2.